Log on, tune in, find out. Another good idea from Cambridge.
See what you got.
That's true. Okay, thank you very much for the invitation to present at this conference. Sorry, I just want to make sure that this is the right place. Right, so this is a joint work with Sergio Leza Serrano, who is here, and we will also jointly present this work. So I'll start and Sergio will continue about halfway. It's about experimental designs for estimating various components, and right at the beginning I will explain the motivation of this work with an example, and then we'll go through as quickly as possible through the background, define some criteria of optimality, spend more time on examples, and discuss the significance of this work. Questions we'll answer together at the end. So in every statistical model, there would be two types of parameters, fixed and random, and the fixed parameters will do quite nicely to explain the mean of the response. At the same time, the variance components are also very important because they tell us so much important things about the source of the variability in the experiment. So the standard classical criteria of optimality are mainly concerned with the statistical properties of the fixed parameters. So the optimality, for example, is typically described as a criterion requiring minimization of the volume of the confidence ellipsoid for the model parameters in the model. For the model parameters. However, the variance components could be indeed the important parameters that need to be estimated. So an example, I'm trying to get used to the technology. The example comes from my relatively short time in industry. When we set up a long screening bioassay, we've got to start by, first of all, doing assay validation. First of all, what is a bioassay? For some of people who may not know, that's an experiment trying to find out the potency of compounds. The way that is done is through putting the dose in a well in one of those plates. So when we screen, we usually test not hundreds but thousands of compounds. So obviously a very large number of plates like these are used, and also observations are taken not over weeks or months but over years, so easily over 2 or more years. So we've got to appreciate the significance of the variance components, the variability due to use of different plates, and also different locations, not just variability on the plate itself. So that is why we start with a validation experiment, and the main aim of this experiment is to set up the main study that is going to last for a couple of years. So we need therefore to estimate as precisely as possible the variance components, identify the best conditions where the variability will be smallest, perhaps do some power calculations, see how we can monitor variability as well. And clearly the compounds that we are going to use to estimate these various components are not important. So the fixed parameters in this case are nothing more than just nuisance parameters. Well, if you look around, you may see more examples, but for this type of experiments. But in this case, what we really want to know at the end is how many plates we've got to use, and on how many occasions we have to test compounds, and effectively what compounds to test. Okay, so a little bit about the background. So what people have done in the past. Not much. In fact, Herzberg and Cox in 1969 pointed out that only 3%, in fact less than 3% of the approximately 800 cited articles were classified as dealing with designs for variance component estimation. And the proportion of papers devoted to this problem has remained small. But we still can point out the existence of two useful reviews. The first one by Curie and Saha in 1985, and another one 16 years later by Curie. What comes out from this work and also from what Sergio and I have been looking at is that most of the work is devoted to specific problems, and the research is therefore very much fragmented. It's not linked to the optimum design theory as such, and in a way there is some rediscovery of ideas here and there. So what we want to do really is to develop the theory for this type of a problem and link it nicely with the optimum design theory. Of course, we want to do it for the most complicated models, for the largest possible variety of situations, but we haven't done it all yet. What we'll present here is the foundation which we're trying to make as solid as possible, not that it is easy even to do that. So there's very much work in progress, but there's still something to show you. So the one thing that comes out of the literature is the recognition that the optimum design depends on the unknown true values of the variance components. So that is a nice similarity with designs for nonlinear models. and here is an opportunity to bring in this type of problems to the theory, to link it to the optimum design theory. Some references which we like to point out, starting with perhaps the first well-structured presentation of the topic by Bainbridge in 1965, staggered nested designs. Then an interesting paper by Giovanoli and Sebastini on experimental designs for the mean variance component models. The title is a little bit too general to what it is actually in the paper, though. That's what we want to do, but we're not ready to do it. First time we know computers being used to search for such designs is in 1991, Delgado and Laya, and a couple of interesting papers by Ankerman with different collaborators in 2002 and 2003. First one on split plot designs and assembler designs. Having said that, of course, what remains is that these are still quite focused on specific applications. So we want to generalize, and we've got to start from somewhere. It's a good starting point would be the linear mixed effect model. And I won't spend much time on the details here because they were already presented. Even the notation is conveniently close to that was already used, except that Professor Bates used, I think, B instead of gamma here. Otherwise, the design matrices for the fixed parameters, beta, and the random parameters, gamma in my case, Z, are X and Z respectively. So we can, of course, combine this into a single term. Sometimes it's more convenient. The observational errors here are epsilon. In terms of model assumptions, the expectation of the response will be equal to X beta, and all random effects will have zero means, so that's why these expectations are zero. We'll assume independent observations as well as independent random effects with variances sigma epsilon square, sigma 1 square, and so on. These are, of course, assumptions that deserve to be revisited at a later stage because we want to be able to do more complicated things quite often. And, of course, when the actual linear part here is not actually linear but non-linear. So the variance of the response, of course, is then given here. There are a number of ways to analyze the data, and this was already shown. So we won't spend much time on this. Just by we'll say that we're interested in the maximum likelihood estimation in this case. But of course, this is another thing that can be easily revisited. So the model given here is the variance covariance matrix here, and the maximum likelihood estimates for the parameters will be obtained by maximizing the likelihood, or somehow easier the log likelihood there. So we want to estimate the betas and also the variance components. And the efficient information matrix turns out to be this. Again, if you go for more complicated models, this is likely to look somehow different. But in this case, it is quite useful and interesting to point out that optimizing designs for beta and for sigma square can be done independently. Of course, we still know that the optimality for the designs for beta doesn't depend on the true values of beta because of the linear part of the model, but that will not be the case when we have more complicated models. And the optimality for sigma square, though, sigma square now is the vector, that's why it's in bold, if you can see it is bold, is the vector of all variance components, so it depends on the actual values. So this is where the design for beta is like a linear problem, and the design for sigma square is non-linear. And this is where we can borrow some ideas, and we will do that now. So if you're interested in, again, in estimating precisely the model parameters, in this case we're interested in the variance components, we can use the optimality idea. Why not? This is the information matrix for the variance components. So the design that will be the optimal will be the one minimizing the determinant of the inverse of the information matrix. Of course, we cannot calculate this matrix unless we make some assumptions about what the true values. Yes?
I'm a little confused about the top formula, that you have both I and J in there, and then you're taking a trace. So does the trace
So
only
the
involve
ijth element of the matrix.
Of the matrix, yes. The I and J is from 0 to R.
Ijth element of the matrix.
But then, if you're taking the trace, you only need the II elements, don't you?
But we're defining this for I and J, so we'll have different traces for each I and J.
They don't cancel out.
Yeah. Okay, we can always discuss later. The thing is that is, well, something like that. I believe that is the information matrix in this case. And what we may want to do is to minimize the volume of the confidence ellipsoid for the model parameters, in this case the variance components. And we cannot estimate this criterion that alone optimize with respect to it unless we make some assumptions about the true parameter values. So we can again borrow an idea from the optimum design theory for nonlinear models and use the local optimality. So to just assume the most likely vector of values for the variance components. Equivalently, we can also, or similarly, we can also adopt the Bayesian, the optimality. That is when we cannot really come up with such a nice vector, but instead we have to present the knowledge about sigma squared through its prior distribution, or in some cases through ranges of plausible values of the variance components, which are defined in this capital sigma. So the point is that we have a well-defined optimization problem, and we can indeed solve it one way or another. We can, of course, do it with different criteria. I want to spend much time because we're kind of running a little bit slower. I don't want to leave less time to Sergio later. So another interesting similarity that is coming up, and we can make use of it. First of all, it can be seen that the optimality for sigma square doesn't depend on the total variability of the experiment, but depends on the proportions of the different variance components.
A short question. You try to find the best z's, right? So your optimal design is about z, right?
Well, it is. It could be more than that. It could be, depending on the type of model you do. You use, it could be that. It could be about sample size calculations equally. It could be part of the problem. So in the case that, in the motivating example, it is, the design is the one which chooses the number of the plates and the number of the occasions which we'll use to test the compounds and how many observations we'll take on each of the plates. That is the simple case. Of course, we can have more complicated case. We can have split plots, in which case some of the predictors are both in X and Z, but that's in the context of this motivating example what the design is, how many occasions and how many plates. You'll have some examples later on coming exactly relate to the motivating example. So because of this observation, we can also see some interesting similarity with another type of experiment that most people would be familiar with, that's the mixture experiment, because in the mixture experiments the response depends on the proportions of the mixture components, not on the total amount. So that is the similarity really. Here though, instead of the response we have the parameter space. And this allows us to summarize results on design construction in a kind of, we believe, a nice way. This is the parameter space for the variance components. In the motivating example, that will be the on the plate variability, within plate variability. That will be the between plate variability. That will be the between occasion variability. So the three sources of variability. And for each combination, of course, we can find the optimal design through solving the optimization problem that I defined on the earlier slide. And then for each combination, we can see which design is the best one. So there will be several designs. Some will be good for these cases, so this will be good for those cases. In this case, what we've done is we've used a different color for the designs which are best for particular combinations. So in this case, this gray color corresponds to a single design which is best for all possible values of the three variance components falling into this area. And this way, we can, of course, see not just how the local optimality works, but we can easily see the Bayesian and robustness and so on. So that is the graphical approach of presenting results that we have adopted. So Sergio will show you more of this and then link with specific examples. Instead of talking about that, though, I will just want to say a little bit about other criteria of optimality. I mentioned the optimality and possibilities to extend. Similar to other design problems for nonlinear models, we might be interested in functions of the nonlinear parameters like C optimality. That is what was mentioned in the previous talk, the AUC or the C max. These examples of optimality of this type. In our case, it will be interesting to look at ratios of variance components. As you see, it's very easy and nicely linked with the general theory of optimum design. One example to illustrate the dependence of the information matrix on the non-variance components. So for the case of two cross models, so we've got two random variables. First one at A level and the other one at B level. So this is what we have to find out in the design construction, what A and B should be. And there's the observational error. The observations for every combination of the first and the second factor will be Nij in general, or for a balanced design, it will be just N. So that is the information matrix in this case for the three variance components. What we've got here is the upper triangular matrix of the information matrix. And I know it's not really easy, if at all possible, to read it all, but the point here is that the elements of these terms depend on sigma epsilon square, sigma alpha square, sigma beta square, through a quite complicated and clearly nonlinear way, even for such a simple situation. But it is possible to derive, and here is how it looks if we have a nested model. So if B is nested into A, and Sergio has derived some results for the interesting situations, including ratios of models, ratios of variance components. So in the case of ratio of variance components, we will be interested in the case where the functions of interest are sigma I squared over sigma epsilon squared, so that we have two ratios coming out of the three variance components. Okay, so I think that's from me, and the next slide will be Sergio's contribution.
Please. Yes, sure. Thank you. Thank you. So these examples are related to the bioassay experiment that was introduced at the beginning. So consider that the bioassay is performed over different occasions that we will call days, and the experimental units, that are the plates, will be measured in different sets of equipment, in different benches in the lab or whatever, and we will call those the readers. So the actual experiment will consist of taking measurements on N plates using B different readers on A different days. In this particular situation, the example one that we just mentioned, the two-way cross model, is an appropriate one. It will look like this. We will include the overall mean and a random effect for days, random effect for readers, and of course the random error, and in this case would be the plate effect. So we have three variance components in total, 1, 2, 3, and as we were discussing just here, in this case the optimum design problem is to choose the appropriate number of days, in this case the A value, and the appropriate number of P readers and the appropriate number of N plates to use during the experiment. So because we are after the locally optimum design, we have to introduce, or we have to provide preliminary values for the variance components, and we do that in this for the sigma square vector, sigma epsilon square, sigma alpha square, and sigma beta square here, and we let them run from 0 to 1 each one, and then we compute, we form the fine grid, in this case 50,000 sigma square vectors of triplets, and if we have a list of candidate designs to test, now we can compute the information matrix, and we can then compute the optimality criterion on that, and then we compare the optimality criterion values across the designs, and we can choose the best design from there. So to finalizing introducing the fundamentals here, we consider the balance designs for ease of presentation, and in that case we can list all the possible two-way arrangements for a given number of observations, and in this case if n equals 24, all these 9 designs are possible. We just avoided to include blocks of size 1 here. That's the ones that are missing. So we have a model, we have the information matrix, we have the list of preliminary values in the grid, and we have a candidate of design of a list of candidate designs, so we can compute now, we can make the computations. And then we present that in this triangular simplex scheme that we already saw. This is set such that on the axis we have epsilon here, and we read epsilon from these diagonals, and we read alpha, sigma alpha square on this axis from 0 to 1 using this diagonal going the other way, and sigma beta square, which is the complement, will be read on the horizontal line going from 0 to 1. So once we have the plot here, all we have to do for the optimality here on the left, we have a optimality there on the right, we just have to choose a sigma square vector of interest and then just map it into the plot and read which is the proper or the optimum design for that particular value. So we have, like, for instance, in this region, D1 is the optimum, and in the optimality, D8 is the optimum there. So actually, if we focus a little bit on the A optimality one, we can see clearly that there is this symmetry line appearing there. And in this case, that line corresponds to a condition where sigma alpha squared over sigma beta squared equals 1. In general, a constant, but because we went from 0 to 1, that constant is 1. So once we are on the line, we can go just above the line or below the line to choose the design. So if we fix the value of sigma alpha squared, right, to go above the line, we will we will be decreasing the ratio because sigma beta square will be growing. And if we go below the line, we will be decreasing the ratio by increasing the ratio because sigma beta square will be decreasing. And now sigma epsilon square will have to be adjusted accordingly because we are in the simplex, so it's just the proportion. So that's an interesting feature here. For instance, let's see, for sigma epsilon square for about 0.7 and below, like from 0 to 0.7, the phenomenon is that the optimality criterion, like A optimality here, it's only depending actually on the ratios or the relative sizes of these two. So depending on which one takes priority, we will go above the line or below the line. So the same phenomenon happens from 0.7 to 0.9 here, but they involve different designs here and there. And again, we will choose above the line for depending on the values here or below the line. And the only interesting remaining bit here is the far corner here, which corresponds to the fixed effects model, because at that point, sigma epsilon square is fairly large, 0.9 and above, and at that point, then these two guys, they do not have a role to play. So on the d-optimality side, we see the same large sigma epsilon square behavior here, although it happens from 0.8 onwards. And on the other side, we just see that d-optimality is much more sensitive to the actual sizes of the variance components than A-optimality here, but on its favor, A-optimality will then be more robust about the misspecification of the preliminary value. Now, this setup is such that we are highly confident on that the value that we choose to map in the plots is actually close to the true value. When that is not the case, we recourse to the Bayesian framework that Alex presented, and that involves actually averaging the criterion values instead of mapping it like that. And we can get to these plots now for the case that there is no specific information about sigma epsilon, sigma square, and sigma square vector. So we can use sort of all the region here for the averaging. And then we set up also this plot such that it is also always the minimum criterion value to be the optimum, to minimize the inverse of the information matrix. So in this case, on the optimality, design number 2 and design number 8 are sort of equally optimum. So we can choose the most economic one. Everything will point out that fewer days will be more economic. So probably we will choose D2, D8, 2 days only, and 6 readers. And on the A optimality, we sort of see the same situation, but involving design 2 and design 1. Another case, probably more interesting, will be to select just a region of the triangle and compute there the Bayesian optimum design. So we chosen this condition, sigma alpha square greater than sigma beta square greater than sigma epsilon square, which is fairly intuitive. And we have this situation now. Again, 8 and 2 appear to be the most optimum, if you like, and on the A optimality side is 1 and 7. If we change the scenario now a little bit, and instead of running the plates directly, we use different brand new plates every time. Then we introduce nesting between the days and the plates. And for that situation, example number 2 that was presented as the nested model is the appropriate one, which looks exactly the same, but the construction of these pits will differ in the construction of the set, the actual set, and then the interpretation is the random effect of plate within days. That's the change. And then we produce the same plots. Now we see that there is no symmetry line anymore because of the nesting. And then again, the optimality seems to be much more sensitive to the selection of the values for the sigma vector, sigma square vector. But what we have here that we didn't have before is that kind of the same arrangement of optimum designs happens. It's just in different like in different relative sizes. And then it's clearly to see how this one is much more sensitive because it spans across a larger area of all the values of epsilon. Let's say this design, all these epsilon values, and also this region and this other region for beta, and this one is more restricted on the beta one. We do the same again for the Bayesian approach for the nested model, and we get design 7 and design 1 to be good for that, and design 1 and 2 also to be an optimum there for when no information about sigma square is available, not specific information. And for the other case of one larger than the other one larger than the other one, design 7 is the best, and design 7 here is also the best. And finally, we also computed the same thing but using the information matrix for the ratios of the variance components explicitly. So the actual form of the matrix changes, and if we plot it like this now, because with three variance components, the ratio is only 2. These ratios are variance component for, let's say, the days over the epsilon or the plate effect. We have the optimality on the left and the optimality on the right, and you see the pattern is the same pattern as in the triangle. Now we can kind of just like zoom in and have a better definition of the regions at which a particular design will be best. And so less emphasis now is put at this fixed effect instant here and here in proportion to the rest. This is for the two-way cross model, for the example first situation of the bioassay, and this will be for the nested for the second case. And we see the same, we find the same pattern, but just better defined. We can better define the regions here. So the natural extension to this, to using the ratios instead of the individual variant components, is that in here we can introduce the interaction effect in the model, recompute, and then plot in a triangular, report in a triangular plot, and we have all the information we need for the random components of this particular model. So that's in general the starting ideas to launch what we want to expand. So as we want to present is that this methodology we can just adopt to the current optimum theory of design, as Alex mentioned, and with the triangular plots or even the two-dimensional plots, it's easy to identify which design is the best one just by looking and plotting, mapping on the plot. And of course, as I mentioned, we can easily extend to different models, and if we have many more variance components, we can have series of plots and distinguish among those. And the interpretation is also pretty straightforward. To extend this work, it is the natural, well, there are probably some natural things, but one that is of big interest is to be able to jointly estimate the fixed effects and the variance components using this particular setup. And for a particular interest of mine, we want to expand into the split plot design structures more fully, which will include using a different variance covariance matrix, and possibly including covariates in the matrix, in the variance matrix and in the design matrix together. And also we mentioned the ratios of the variance components, but only the ratios with respect to sigma epsilon square. But we can also, of course, take ratios over the total variability. So one variance component over the sum of all the other three, for instance. And we will also like to explore the cases for general variance models, like exponential variances or something like that. And the cream of the crops will be to move to the nonlinear model, either in the random effects or the fixed effects or both. both probably is way too much. But I think that's the end of the presentation. So if you have questions,
Questions? Please.
yeah.
Doug?
I hate to keep harping on the same point, but what would happen to the information matrix if you didn't look at the variances? If you looked instead at standard deviations or something like that? Because the information matrix tells you about the local behavior, assuming that locally the likelihood would look quadratic.
Yeah,
It
that's
doesn't.
large sample. Yeah, symptotic, yes.
Yeah.
Well, I guess the answer now, by far correct one, is probably will be in this area here to extend the development to include, let's say, any type of variance definition. So the standard deviation easily falls into that, but we can have any other sort of variance functions. So the answer probably is, at the moment we don't have an answer, but we have identified that that is a very natural extension to this.
As far as I understand, if you talk about standard deviation, all triangulars disappear because you don't have this nice sum equals 1, right? So at least
that's
geometry
true.
disappears. And instead of this linear interpretation, you may have non-linear optimizations when you want to estimate optimal standard deviations, correct?
Yeah, probably that's one of the easiest consequences of this. Probably there are ways around to remap
Right.
the new region into the triangle,
But
then it will be
optimal
like a
designs will
twisted
change.
triangle or
The
something.
optimal
like that.
designs will change. That's
Yeah, definitely. But yeah, the concern is not necessarily that they change for us. The concern is to pinpoint the best one, whatever it is.
In the Bayesian approach, can you ignore sigma squared and just assume a prior for the relative proportions of each variance as a proportion of the sum of the whole?
Well, I guess as we presented it, that will be like to use the case for the ratios
Yeah.
and then do the averaging on that, but we didn't present here. We just present the individual ones. Yeah, I guess.
Could you assume a Dirichlet prior for sigma alpha squared over the sum of the variances, sigma beta squared over?
Yeah, I think, yeah. But now the region will not be very well defined as before, but I think we can also do that. We define the preliminary subset of ratios, and we can average from those. Yeah, I think so. You're asking me to think here, so I'm not completely sure.
I have a question. In a standard variance component model, z's are orthogonal, so z prime z is an identity matrix, right?
Yes.
In some cases, like in the book of Rao and Cleffe, they continue this model and assume there is no orthogonality. In your example, you assume orthogonality, right?
Yeah, we use the simplest one,
Right.
which is the two-way
Right. Did you
two-way
try-
balance.
Yeah.
Kind of means orthogonality to some
Exactly,
extent.
exactly.
So the information matrix as we presented here accounts for all the assumptions we made, which are the standard
Which is
Gaussian,
right?
Gaussian linear model things. But the actual form of the matrix involves the derivatives of the inverse of the variance covariance matrix, and then of course we have the i's and the j's. The II will correspond to the weight of one variance component on the matrix, and the other one is the other weight. And then because we go I and j's and so forth, we get all of them crossed. So part of this further work will include, or it will force us to use the general structure of the variance covariance matrix, which may or may not be diagonal, and may or may not be the whole model orthogonal, which most likely will not be. But the optimality theory in general is not very concerned about orthogonality, because in general we are orthogonal enough if we have a good way of finding the optimum design.
Questions? Yes, please.
I think you've already answered my question in a sense, but the patterns that you showed us in the triangles and in the normal 2D plot were very clearly defined, and I guess there's no way of getting the boundaries explicit.
Well, we try to explain that the boundaries, they represent very particular conditions. Like in the simplest case, we have the very well-defined symmetry line that corresponds to the ratio being a constant. So in the other cases, probably it's easy here to do. But here we have similar lines, so this will correspond to the ratio being also constant but different from 1. And then will be this one or that one or that one will be for a different ratio constant. So constant is any line there. But we don't actually choose from the line, because then any design here of these two is the best. So we just move a little bit and we can choose which design is best. Yeah, the general sense is choose the most economic one. I don't know if it does.
Can you get those lines explicitly without doing all the computation?
No, I'm not sure I understand the question now, because I mean, anywhere if you set the ratios to be constant, you are automatically defining the line.
You put a boundary there, that was the...
Yeah. It's like we said, we keep sigma alpha square fixed, and then we can see the line appearing there. So you fix sigma anywhere and vary the other one.
But if you
Well, not
pick
vary the
sigma
other one,
right-
choose the one that makes constant.
If you pick sigma right where the chartreuse hits the brown,
Repeat?
okay, look at where the chartreuse meets the brown. Okay, there, yes.
Yeah.
So can you
Yeah.
write, that line where it meets the brown, where the chartreuse meets the brown, can you write a formula for that? Can you tell what sigma?
Oh, it might be possible, if I
Characterize the
don't
line.
mind finally saying something. It might be possible, but the thing is that we wouldn't be able still to find a general result that is the same for all n. We remember this is for 24 observations and for specific design structure. So it could be possible to derive for that particular case, but it would not be as general and therefore not as useful as it may look. But I think it's possible to do it though. But what would you do with this formula at the end? That's the question.
Yeah, but that will be very specific for the particular
Yeah,
model, for the
that's
particular
specific.
candidate list of designs that we created. Of course, we choose the very simplest example, but the candidate list may not just include these designs. It can include any other design.
Yes, and
As you
let's
wish.
make it last question, Barbara.
Thank you. I like these pictures. It would be interesting to see the overlapping of the two. And then you could see for what conditions or what values of sigma squares you would have both E and A.
Okay.
That's a common.
Yeah.
Because
you can
sometimes
overlay
it's
them.
good to have
easy to see.
both, and that,
Yeah.
and then if you could think about the boundaries for these, that might be.
Yeah, honestly, we didn't think much about the boundaries because we said, well, you very rarely want to be on the boundary. But yeah, that's a fair question. Though. Thank you.
Thank you again.